Hi everyone, today we're going to talk about autoionization of water and the pH scale. This is related to two learning objectives from the College Board, basically to learn what is pH, to describe the concentration, and also to calculate pH. Water is amphoteric. It can act as an acid or base to donate or accept a proton. The ionization of water is endothermic, where heat is a reactant, so we can have two water molecules to ionize into hydronium ion and hydroxide ion in the proton transfer. Or simply put, we can say heat added to water to be ionized into hydrogen ion and hydroxide ion. Now when we write the equilibrium constant, we call that ion product constant, Kw, which is equal to the concentration of the hydronium ion times the concentration of hydroxide ion, or the H plus times OH minus ion concentration, which is equal to a constant 1.0 times 10 to the negative 14 at 25 degrees C. It will be good for us to remember this number to be used in calculations. So, because water is neutral and hydrogen ion is equal to hydroxide ion concentration, each having 1.0 times 10 to the minus 7 molar. Because Kw is temperature dependent, so at a higher temperature, that means the reaction goes far more to the right, dissociating water molecules to form a higher concentration of hydrogen and hydroxide ions. Therefore, the Kw value will increase at a higher temperature. When the hydrogen ion concentration is greater than the hydroxide ion concentration, solution is acidic. However, when the hydrogen ion concentration is less than hydroxide ion concentration, solution is basic. And when they equal, solution is neutral. Now we can calculate hydrogen ion concentration by dividing Kw by OH minus ion concentration, or vice versa, the hydroxide ion concentration by taking Kw divided by H plus concentration. pH scale. Now the concentration of hydronium and hydroxide ions are reported as pH and pOH, where pH is negative log of base 10 of the hydronium ion concentration, and pOH is negative log of base 10 of hydroxide ion concentration. So if you look at pH scale, which goes from 0 to 14, and you relate that to the corresponding hydrogen ion concentration, a pH 0 is equal to 10 to the power 0 of hydrogen ion concentration, which is 1, or pH of 14 is related to 10 to the negative 14 molar of the hydrogen ion concentration. When the pH is less than 7, we have an acidic solution. When pH is equal to 7, we have a neutral solution. And when pH is greater than 7, we have a basic solution. Please note that an increase of 1 on the pH scale means a decrease by a factor of 10 in the hydrogen ion concentration. Now, in the biological system, the hydrochloric acid from the stomach can come into contact with the esophageal lining and creating an irritation that's called heartburn. Heartburn can be neutralized by taking antacids. And a lot of doctors are using pH reading that's transmitted by a wireless pH sensor attached to the patient's esophagus to diagnose and treat this GERD disease. Another term that we have heard often of is ulcer. We have a thick layer of mucus lining the stomach wall and protecting it from hydrochloric acid and any gastric juices in the stomach. So if the layer is damaged by bacterial infection, the stomach juices will then come into contact with the stomach wall and digest it, creating a burning pain called ulcer. Acidic food and aspirin can irritate ulcers, so these are all pH related in our body system. pKw. Now, as you know, the ion product constant, Kw is equal to hydrogen ion times hydroxide ion concentration, equal to 1.0 times 10 to the minus 14 at room temperature 25 degrees C. So we can take the negative log of the Kw as well as the negative log of the hydrogen ion and hydroxide ion concentration. And so negative log of Kw is equal to negative log of hydrogen ion plus negative log of hydroxide ion, which is equal to negative log of 1 times 10 to the minus 14. Putting all that together, we now have a new equation, pKw is equal to pH plus pOH equal to 14, and we'll be using that equation in a number of calculations. So for pure water at room temperature, pH is equal to pOH equal to 7. Water is neutral. When the pH value increases from 0 to 14, that means the pOH value will decrease from 14 to 0. Let's pay attention to the significant digits of pH. When hydrogen ion has 2 sig-fig, the pH carries 2 decimal places, and that's the rule. For example, hydrogen ion is equal to 1.0 times 10 to the minus 2 molar. Here we have 2 significant digits in the 1.0. Well, when you take the pH, it is equal to negative log of 1.0 times 10 to the minus 2, which is then reported as 2.00. Note the 2 decimal places. To convert pH into hydrogen ion, we take 10 to the negative pH. So if you have a pH of 2.8, which has 1 decimal place, then the hydrogen ion concentration is 10 to the negative 2.8, all with 1 sig-fig, 2 times 10 to the minus 3 molar. Practice problem number 1. Find the pH and pOH of hydrochloric acid of 1 times 10 to the minus 5 molar. Is the solution acidic or basic? Well, HCl is a strong acid that ionizes completely. So the initial concentration of HCl is also equal to the hydrogen ion concentration, which is 1.0 times 10 to the minus 5 molar. Now we can take the pH, which is 5.00. And the hydroxide ion concentration, we can calculate it by taking Kw divided by hydrogen ion concentration, which is 1.0 times 10 to the negative 14 divided by 1.0 times negative 5, and we get 1.0 times 10 to the negative 9 molar. So the pOH is negative log of 1.0 times 10 to the negative 9, which is 9.00, 2 decimal places. And the solution is acidic because the pH is less than 7. Practice problem number 2. What is the pH of 0.012 molar solution of strontium hydroxide? What are the major species in the solution? Strontium hydroxide is a strong base that ionizes completely. So we can write the equation as such, where you get 1 mole of strontium 2 plus ion and 2 moles of hydroxide ion. So the hydroxide ion concentration is 2 times that of the strontium hydroxide, which is 2 times 0.012, which is 0.024 molar. Therefore, the pOH is based on the negative log of 0.024, which is 1.62. Note that we use 2 decimal places in the pOH, and the pH is calculated as 14.00 minus pOH, which is 12.38. The major species are strontium ions, hydroxide ions, and water molecules, since the strontium hydroxide ionizes completely. Practice problem number 3. What is the pH of the solution when 50.0 ml or 0.302 molar NaOH is mixed with 150.0 ml of calcium hydroxide with a pH of 11.28? Now, sodium hydroxide ionizes completely. So if you want to calculate moles of hydroxide ion, this is equal to the molarity of NaOH times the volume, which we obtain to be 0.0151 moles. Regarding the calcium hydroxide, we can start off with a pH of 11.28, finding the pOH of 2.72, then find the hydroxide ion concentration of 10 to the negative power 2.72, which is equal to 1.9 times 10 to the minus 3 molar. Now we calculate the moles of hydroxide ion in calcium hydroxide, which is 1.9 times 10 to the minus 3 molar times 0.150 liter, and we have 2.85 times 10 to the minus 4 moles. Because it's a mixture, so we add up the number of moles of the hydroxide ions coming from sodium hydroxide and calcium hydroxide and divide it by the total volume. Now we have a new molarity of 0.0769 molar in the mixture. And then we can calculate the pOH, which is 1.114. And from that we derive pH by subtracting pOH from 14. We have 12.886. In practice problem number 4, what's the resulting pH of a solution when 35.0 ml or 0.2 molar HCl is mixed with 55.0 ml or 0.175 molar NaOH? Now this is a neutralization reaction of a strong acid and strong base, so we can write the net ionic equation as H plus and hydroxide to make H2O. It is also a limiting reactant problem. We can calculate the millimoles of each species. It's easier to maintain millimole because later on we're going to divide it by milliliter in the mixture. So it is equal to 7.00 millimole of hydrogen ion and 9.625 millimoles of hydroxide ion. Then we realize that H plus HCl is the limiting reactant, so that 7.00 millimoles will be used up. And then we have 2.63 millimole of the hydroxide ions left. And when we determine the new concentration over the total volume of the mixture, we now have 0.0292 molar. pOH therefore is 1.535 and pH is 12.465. So in summary, what we have learned today is 1, the definition of Kw, the ion product constant for the ionization of water. 2 is the relationship between Kw and H plus ion concentration and OH minus ion concentration. Now we further define the acidity or alkalinity of a solution using the pH scale. And we learn how to calculate the pH of a strong acid and a strong base. And then we talk about the application of pH to the biological system, such as the chronic heartburn disease. I hope that you find the video helpful. From the team of MLCA, we would like to thank you for watching our video and hope to see you again next time.